GameSat.com. Quad tree collision detection, another divide and conquer game algorithm. Quad tree is another natural recursive problem because it solves collision detection by dividing the problem into quarters, then calling itself to solve for the correct quarter. It's twice as good as binary search, which only divides in half. Basically, we're talking about the same concept. Divide my search area into 4 parts instead of 2 parts like binary search does. Clearly a divide and conquer algorithm. We're going to divide into 4s or quarters. So here's the problem. We want to determine if and where Mr. Happy Face collides with any star on the video game screen. Here is our screen. Think of those stars as objects, right? We're going to have objects that we can run into on the screen, and as Mr. Happy Face moves around, we want to know when he bumps into one of these star objects. Wrong way to do this is to compare Happy to each and every star and see if they overlap. Compare Happy Face to this star and this star and this star and this. That is the wrong way to do it. We don't want to compare Happy Face to everything else on the screen. That's just going to take way too much time. So the right way to figure out collisions, who does Mr. Happy Face collide with, is to use quad tree. Quad tree says divide the screen into smaller and smaller quarters and only check the correct quarter. So let's see what we mean by that. Boom, I've overlaid these green lines on the screen to kind of divide my screen into quarters. I've divided the screen into 4 quadrants. Clearly Happy only resides in one of those quadrants. What does that mean? It means I only have to check the star objects in that quadrant for collisions. I'm going to ignore the other 3 quadrants and recursively call quad tree for the correct quadrant. I don't have to search here. I don't have to search here. I don't have to compare here. None of these need to be compared because Happy Face is in this quadrant. Recursively call ourselves for that quadrant. Now, that is a lot of star objects that do not need to be checked, but there's still many in the current quadrant. What to do? What to do? Well, if it worked once, let's recursively do it again. Let's call quad tree recursively and say, divide this area into quadrants. So divide the smaller section into 4 smaller quadrants. Clearly, Happy only resides in one of these subquadrants. What does that mean? It means we only have to check the star objects in that subquadrant for collisions. Ignore the other 3 quadrants. I don't have to check here or here or here. That's 6 more checks I've eliminated from my test to see if Happy Face has collided. Let's recursively call quad tree on the correct quarter, this quarter only. Bang! More star objects that do not need to be checked. At this point, there are so few star objects in our quadrant, time to check for collisions. And it, in fact, finds those 2 stars collide. There's a collision right there. There's a collision right there. Now, how many times it divides in quarters depends on how many screen objects there are. The more objects you have, the more dividing you do. If I was trying to check 1,000 different objects, I'd have to subquadrant many different times. I'd recursively call myself more. The total number of objects you want to see if you collide with determines how many times you recursively call the quad tree algorithm. Note, I restored the stars. I put the star objects back. They didn't actually go away. They were just hidden to show that I don't have to check that. I don't have to see if Happy Face ran into a star that is in a different quadrant. In a complicated game with 1,000 possible collisions on the screen, quad tree can greatly improve performance. Instead of checking 1,000 different objects to see if you collide, maybe you can get it down to 5 or 6. Repeatedly divide the screen into quarters and only check the quarters for collisions. So let's move Mr. Happy Face and do it again. So as Mr. Happy Face moves across the screen, he enters a different quadrant. The quad tree selects a different quadrant and recursively calls itself on the new quarter. Bang, I don't have to check any stars in that quadrant. Since this quadrant has so many star objects, again, I'll recursively call quad tree again and divide that section into quarters. See the recursion? I'm going to drill down, selecting the proper quadrant until what? Until we reach a reasonable number of objects to check. At this point, there are so few star objects in this quadrant. Stop trying to divide and conquer by checking for collisions of star objects in the quarter. And in this particular case, no collisions were found. The only 2 star objects in the same quadrant had to be checked, but they did not collide. So rather than check all of these star objects, I only had to check the 2 that were closest to Mr. Happy Face. Note again, the star objects did not actually go away. They were just hidden while I showed you how the algorithm works and showed you that you do not need to check for collisions for objects that are outside your quadrant. In a complicated game with 1,000 possible collisions on a screen, quad tree can greatly improve performance. It's the difference between a sluggish game and a fast game. I must admit, it's an overly simplified explanation of quad tree algorithm. You're going to need a data structure course to learn how to build the tree properly. See you in the data structures class, maybe? Hopefully so. So there you have it. That's recursion. Recursion is used a lot in game design. It's important to understand how it works with the stack and how it reduces a problem from a big problem to a smaller, to a smaller, to smaller. Good recursion means every recursive call should reduce the size of the problem. Binary search chops it in half. Quad tree chops it into quarters. To wrap it up, recursion is simply a method that calls itself.
GameSci.com